Okay, here we're going to talk about these practice problems that I sent out, several pages worth of them, but part of that's because there's pictures. And I have this PowerPoint of the answers, and I'm just going to talk my way through how you do these various problems so that you hopefully can understand them a little better if you were unable to get them correct. So the first problem here is this ball either falling off of the hill or rolling down the hill in a couple of steps. And the first thing you needed to do was take note in the paragraph that it is a 2-kilogram ball, and that is important. And then similar as we discussed with the roller coaster problem in notes, the first place we need to start is the place where we know everything, which is up here at the top. We're told there's a potential energy of 100 joules and a kinetic energy of 0 joules. Sorry, 100 potential and 0 kinetic. So when you add those two together, you get a total energy of 100. And that means that every step in the diagram, we need to get a total energy of 100. So that's easy at these 2 steps on the ground, right? The ball has reached the ground, so its height is 0. So if its height is 0, then its potential is 0. We know all the energy is in kinetic. And then we can use the kinetic energy equation, 1/2 mv squared. Conveniently, m is 2, so 1/2 of 2 is 1, so it's just v squared equals 50. This square root, sorry, this is doing this point, but it's mv squared equals the kinetic energy. So in this case, we have 100 equals v squared, so the square root of 100 is 10. So we discovered that both of these have the same velocity. Of course, this one would be at an angle, and this one would be straight down. On the other hand, these 2 objects, this one we're told has a potential of 50, which leaves us with 50 for kinetic. And since these 2 are at the same height, then we know this one has a potential of 50 and therefore a kinetic of 50. So then when we take the square root of 50, 7 squared would be 49. So it's just slightly more than 7.1 meters per second. So the text there in red is filling in all of the blanks, and hopefully this one makes sense to you now that I've explained it. It's really about energy conservation and then taking the kinetic energy and using it to find the velocity. Number 2, if friction forces are present on number 1, what's going to happen? Well, some of the energy is going to be taken away by friction, which means we'll have less kinetic energy at the end and we'll be going slower. So the answer to this question is, would the energy of the ball just prior to striking the ground be the same or more or less? It would be less because friction would take away some of that energy. 3, 4, and 5 are multiple choice questions. You just have to read them carefully. As the object moves from A to D across the surface, the sum of the gravitational and kinetic energies is going to stay the same, right? Energy is conserved. So even though from A to D, it goes down and then goes back up, its sum of kinetic plus potential will stay the same. Just like at every point in number 1, the sum of kinetic and potential stayed the same. Again, we call that mechanical energy. Number 4, the object will have a minimum of gravitational potential at which point? Well, that would be point B, right? Gravitational potential depends on your height. So wherever he's lowest, that's where he's going to have the least amount of gravitational potential. And then the object's kinetic energy at C is less than its kinetic energy at point, so the choice was actually choice C, which is describing choice B. Question 5 is just worded a little oddly. C is the second lowest point, so it's going to have the second most kinetic energy. So its kinetic energy is smaller than at point B. Point B is even lower, which means it has even less potential and therefore more kinetic. So that's just asking you some energy questions in multiple choice form. So that's the first page. Moving on, the second page has some important things. We discussed this a little bit in lecture. Last week, the idea that kinetic energy is a 1/2 mv squared relationship. So 6 and 7 are both asking about this effect in very practical ways. The driver's license exam says if you're going 50 and you skid to a stop in 15 meters with locked brakes, how far will you skid if you're going 150? So a couple different ways to think about this. if 50 is our x, then 150 is 3x. What you should not do in this problem is try very hard to convert it into meters per second. That's not necessarily not helpful. It's really more of a conceptual problem. If we are going 3 times as fast, 150 is 3 times 50. If we're going 3 times as fast, we look at our kinetic energy equation, we put in 3 times the original velocity. 3 squared is going to give us a factor of 9. So 3x squared is going to be 9 times bigger than just x squared. The 1/2 and the m are the same in both cases. So we have 9 times as much energy at the higher speed. They didn't ask us how much more energy. They asked us how long it took us to skid to a stop. Well, remember, our change in energy is equal to the work done. Work done is force times distance. Our brakes are going to lock in both cases. Therefore, the force is going to be the same in both cases. If we have 9 times the kinetic energy, then 9 times the work is going to have to be done to stop us. And if our brakes are already locked, that force can't change, so we're going to need 9 times the distance. So you take that 15 meters, you multiply it by 9. 15 times 9 is 135 meters. You can also do it if you don't like these x's and variables. 50 squared is 2,500. 150 squared is 22,500. You divide those, it's still a factor of 9. It's going to be a factor of 9 because there's a factor of 3 difference in the velocity. That's just how the squareds work. It's going to square whatever factor, whether it's 2, 3, 4, 1/2, 1/5, it's going to square that effect. So that's what they were trying to get at in number 6, and many people have trouble understanding number 6 because it's really more of a conceptual question, but being asked with numbers. Number 7, very similar question, although many people did better on 7 than 6 because there's no numbers at all, so you know it's got to be a conceptual question. If you throw it into the hay with twice the speed, again, we have the same situation. 1 times the speed, which we're going to call v, gives you a certain energy. Twice that velocity will give you 4 times the energy. So we'll need to have 4 times the energy instead of just the energy, and therefore we'll need 4 times the work, and therefore we will go 4 times as far into the hay as if we don't throw it twice as fast. So again, just trying to drive home this idea of the squared relationship of energy. This is why we have speed limits. This is why we have low speed limits in residential areas, because it does in fact take you a significantly longer time to stop if you are going faster, and that is because of the kinetic energy relationship. The other picture on this page is similar to number 1 on the front, similar to our roller coaster problems. Again, only this time they're asking you for the kinetic energy, the potential energy, the height, and the velocity at every single point. So again, we're going to go to the place where they give us everything. Again, this happens to be the highest point. So if our kinetic is 0 and our potential is 450,000, we know that our total energy, when you add those together, is 450,000. And so at every step, our 2 numbers have to add up to 450,000. And we see that that is true. We're also told that the mass in the problem is 1,000. So if we have 450,000 joules and a mass of 1,000, plug in 9.8, you plug in h, you're going to get 45.9 meters. 0 kinetic energy will yield 0 velocity every single time. Here in the middle, when it's kind of divided at the top of the loop between potential and kinetic, you do subtraction. Again, the total should be 450. So you do subtraction. 450 minus 200 is 250,000. And then you use your potential equation and you use your kinetic equation to find your height and your velocity. And then finally, at the end, of course, your height is 0. So you know your potential is 0. So all the energy is kinetic. And then you just use your kinetic equation with the 1,000 mass, and this time with 450,000 in for your energy, and you solve for this one is written for the middle one, which would give you 22.4 meters per second. This one will give you 30 meters per second. So that's that one, and that takes us through the end of the second page. The third page begins with another graphical one. this time of a skier skiing down the slope, and they actually gave you the energies at every point, both energies. But you can see from those that they always add up to the same number. 0 and 50, 20 and 30, 35 and 15, 20 and 30, 50 and 0, always add up to 50 in every case. And then they ask you to calculate the speeds at every location. So that's just a matter of taking your kinetic energy and plugging it into the relationship, 1/2 mv squared. The mass here of the skier is told to be 50. So 1/2 of 50 times v squared equals whatever our total is. 20 at B, 35,000 at C, and so on all the way through. You'll notice that B and C are at the same height, so B and C are going to get you the same velocity. Okay, and E is going to give you the biggest velocity because you're the lowest. You've got all of your energy now in kinetic, and A, of course, gave you the smallest velocity when you had no energy in kinetic. So again, pictorial. There's a lot of pictorial problems in this chapter. It's about height and speed, and height can very easily be shown in a picture. Number 11, object which weighs 10 newtons is dropped from rest to height of 4 meters above the ground. When it is in free fall for 1 meter, what is its total mechanical energy with respect to the ground? So again, key here is they ask for mechanical energy. Mechanical energy is the sum of potential and kinetic. And as the object drops, its potential will decrease, but its kinetic will increase. So its mechanical, which is the sum of the two, will stay the same the whole way down. So the answer to the first question is it is asking us for the total. So what we can do is we can simply go back to the top. That's where it's the easiest, right? So it hasn't dropped yet. It's got a height of 4 meters and 10 newtons. 10 newtons is actually the mass times the gravity, right? 10 newtons is the weight. We kind of discussed this when we talked about the ladder question with Mr. Rassi in the notes. You can go back and watch that if you need to. But the weight of an object is mg, and then if you lifted it a certain distance vertically, that would be the height. So you'd end up with mgh. So 10 times 4 would give us 40 joules. 40 joules. Why don't I have that written here somewhere? Anyway, 40 joules is supposed to be the answer to the first part, but you are supposed to understand that the energy has not changed. The mechanical energy has not changed as it is fallen. The second question is, what is its velocity after it's fallen 1 meter? So after it's fallen 1 meter, it is at 3 meters of height instead of 4 meters of height. It doesn't have 40 joules anymore. It only has 30 joules. So 40 minus 30 would give us 10. Or if you think about it in terms of change in height, mg delta h, that's a change in potential. That's going to be our gain in kinetic. It's 10 joules. The potential energy lost, it's kinetic energy gained. So then we're going to need to plug it into the kinetic energy equation. But we need the mass, okay? So we got to go back and say it was 10 newtons. 10 newtons equals mg. So 10 divided by 9.8 comes out to be about 1. So that's the mass. We don't stick in 10 for our mass. 10 is our weight. Weight and mass are different. We hashed that earlier in the semester. And go type in the difference between weight and mass into YouTube, and they'll show you videos reminding you of what that difference is. But we have 10 joules of energy lost from potential and turned into kinetic. So 10 joules of kinetic equals 1/2 mv squared. That's our kinetic energy equation. We bring the 2 over, we get 20. We divide by the 1, we still get 20. We take the square root of 20, and we get halfway between 4 and 5, right? 4 squared is 16, 5 squared is 25, so 20 is going to be halfway between 4 and 5, roughly. 4.4 meters per second. Keep trying to scroll, and I can't do that. Number 12, during a certain time interval, a 20 Newton object free falls 10 meters. The object gains blank joules of kinetic energy during this interval. Again, the key here is to appreciate that 20 newtons is already got the m and the g included, okay? So mg and the delta h, it drops 20 meters, so it's 20 times 10, it's 200 joules of kinetic energy that has been gained. 200 joules of kinetic energy that has been gained. Don't do 20 times 10 times 9.8. Again, this is 20 newtons, not 20 kilograms. If it had been 20 kilograms, then you would have multiplied by 9.8, but it's 20 newtons, so the 9.8 is already built in. Newtons include both mass and gravity. Number 13, a 200-gram bullet is thrown upward, the initial kinetic energy of 10 joules. What is the maximum height the ball will attain? So if it starts out with 10 joules of kinetic energy, at its greatest height, it's going to have 10 joules of potential, right? Kinetic at the bottom equals potential at the top. When it reaches the top, it's not going to be going up anymore, and it's not going to be falling yet, so it's going to have no kinetic, so all the energy is going to be potential. So 200 grams is 0.2 kilograms, so we need 10 joules of potential, and we want to know the height, so 10 joules of potential equals mgh, where the m is 0.2. We had to convert our grams into kilograms there. So we got 0.2 times 9.8 times.
A couple more practice problems here. We've got the pendulum and the bullet. The bullet is embedded in the block. It's fired at the block. How fast was it traveling just before impact in order to raise the block by this amount? So we look at the energy involved here, the kinetic energy of the bullet, the potential energy of the bullet and the block together. We know how high it went. This is one of those unique situations where we know the afterwards and we don't know the before. So if it rises 0.22 meters, then it's going to have potential energy of mgh. We have the h, we know gravity. The mass is going to be the combined of the 3 kilograms and the 10 grams of the bullet, which 10 grams of the bullet hardly contributes, right? It's 3.01. 3.01 times 9.8 times 0.22. That's going to be the potential energy that it ends up with. So how much kinetic energy did it start with? We work all of that essentially backwards. 6.49 joules from the right side has to equal 1/2 m. This is this 10.5 grams converted to kilograms. It becomes 0.0105. So very small number. Bullets don't have very much mass. 1/2 of the mass of the bullet times v squared. So we multiply the 2 over, we get 12, almost 13 something. We divide by a very small number, we get an even bigger number, but then we have to take the square root. So we get 35.2 meters per second as the velocity of the bullet coming into the block. So it was about setting the kinetic equal to the potential in a little bit of a different type of orientation. 15, Sheila, running at 5.3 meters per second, grabs a vine hanging vertically from a tall tree. How high can she swing upwards? So this is a Sheila or a Tarzan problem. You grab the vine and you swing upward using your kinetic energy to swing up. So very similar to the bullet and the block problem. The difference here is our mass doesn't change because it's the mass of Sheila and it's still the mass of Sheila. The vine does not add anything. The other odd thing that's different from problem 14 is we actually aren't given the mass. No mass is given. But we're just like the cantaloupe problem that we did in the notes. If we're talking about the same object in both positions, then the mass is going to cancel out. Her kinetic energy before is going to equal her potential energy after. It's 1/2 mv squared. We're told the velocity she comes in at, 5.3. And then it's mgh. We don't know h. But we've got the m on both sides, which is the same. So we divide by the m drops out. We have 1/2 5.3 squared equals 9.8 h. And we get an h of 1.43. And finally, the last question here is similar in some ways to the slide that we did in the notes. We got a block sliding down the ramp with a certain speed. What work is done by gravity? So when you want to think about work done by gravity, gravity's force is always going to be mg, right? The mass of the object times gravity, and the distance gravity is going to actually apply that force through in the direction of gravity, right? I mean, this is a situation where the block is actually sliding sideways down the hill, but gravity is always pushing straight down. So it's really the straight down motion that gravity is affecting. So the work done by gravity is equal to the change in the potential energy. It just always is. And if that number is negative, if you have actually, well, we think of gravity as doing negative work, right? Gravity pulls things down. The final height is going to be lower than the initial height. So the work of gravity is always negative. If a person lifts a block up, then you're doing, gravity appears to be doing positive work. Gravity doesn't do positive work. Gravity does negative work. So the first part of this problem is simply doing mgh. That is the work done by gravity. That is also the potential energy the object started with, and therefore it's the beginning of the second part of our problem as well. The second part of our problem is what is the work done by friction. This is just like the Carl slide problem. How much potential energy does the block have at the top? We already did that, 95.3 joules by doing mgh. And the potential energy at the top is going to equal the kinetic energy at the bottom plus the work done by friction. So we were given a velocity, 3.25. So we do 1/2 of the mass, 2.32, times the velocity squared. That's going to give us the kinetic energy. So 95.3 joules to begin with, only 12.3 joules in kinetic energy at the end. So you subtract that. Friction did a lot of work, 83 joules worth of work on the object. And so, or don't let those two numbers confuse you, right? Gravity did negative work, the friction did positive work. That's why we have energy left over for the block to be moving. We don't think in terms of gravity doing work very often, but they ask that question because sometimes they want you to think about it in that way. So